The second video today is about probability distributions. So in my very brief introduction to the rules of probability and how you combine different kinds of events, I talked about how you can get different patterns by combining different kinds of random processes into new meta processes. So we're going to talk about some of the probability distributions that occur commonly in statistics and in nature that we see that are the results of combining different kinds of results together. So first of all, there are some things that all probability distributions have in common. One is that the total area is equal to 1. So what we're talking about here is all the possible outcomes from a random process. And there are no negative values, again, because it's probability. And then each of these curves represents a different kind of probability distribution. And things to look at about them is where their peak is. So these two have pretty sharp peaks. That has a shallow peak. This one doesn't have a peak at all. That one has a low peak, how sharp, but it does have a peak, and is it symmetrical, right? So that one's not symmetrical, that one's not symmetrical, this red one, this orange one, and this blue one, those are all symmetrical. So they have different shapes. And different kinds of probability distributions with similar shapes and similar mathematical underpinnings are called families of probability distributions. And they have a lot of features in common. So there's two ways to plot a distribution. The thing that I'm showing on the left here, the probability mass function, shows, notice these are continuous distributions. It shows sort of the height that you expect that probability distribution to have at a given value. So this is saying that 4s are more common in this orange distribution than 1s or 9s. In this one, the most common outcome is in the 1, near, a little bit less than 1, but near 1. So if you take this and you add up, you continuously add up the area underneath it, you get a cumulative density function. So you can see this rises quickly here, where this is high, that's where the steep part is, and then down here you're not adding very much, so you're already close to 1, and it stays about the same, right? So there's 2, you're almost done with it. See, this blue one is horizontal here, so it's 0 before 2, and it goes up in a straight line until you get to 7, and then it goes straight across. So these are called cumulative density functions. They start at 0 and end at 1. These generally start at 0, go to some middle value, and then drop down to 0 again. An important thing to note about a probability mass function is that even though it looks like the sort of bar graphs that we were doing, showing the counts or frequencies or proportions of different outcomes in the dice rolling lab, these, since they're continuous, when we're talking about a probability, this isn't showing the probability of rolling a 1, getting a 1. The probability of getting a 1 is always 0 because that's a single slice. You have to talk about the area here. So the probability of getting within 1, like 1/1000th of a 1, or something like that. So that would be a region 2/1000ths across, and then a certain height here. So you have to have a start and a finish on the x-axis to describe an area. So you can actually have, if you had a distribution like this, it could actually be above 1 if it was really skinny and like only between two small points. We'll talk about this later. So the probability mass function doesn't show you the actual probability, but it does show you the upper bound of the area that describes the probability of a value occurring in a region. So, when we want to calculate one of those curves in Excel or in Google Sheets, we can use a function. So if we want to know the probability mass function, then you can say, so here's the value -1. If we want to know what the probability of observing something in the -1 area, it will, the upper bound of that, it will give you, you say like norm dist A2, false. And then if you want it to be the cumulative distribution, you do the same thing, true. And you can fill those down. So this dist func is different for every probability distribution. and there may be some extra arguments in addition to know, so we can know what the properties of that particular distribution are. And we'll talk about those in a second. So there are 3 specific probability distributions that I want you to know about at this point in the course. The first one is the most important, and I actually talked about that briefly in an earlier spiel, the normal distribution, or bell-shaped distribution, or Gaussian distribution. So it's the most important probability distribution. It has some really nice mathematical properties, which we'll not go into, and it's defined by 2 parameters, where the center of the bell curve is and how wide the bell curve is. Those are called the mean and standard deviation. We'll talk about those next week. They all have the same bell shape. They're symmetrical, so everything on the left is identical to the thing on the right. They're unimodal, which means there's only one highest point, and they asymptotically decrease to 0 on both tails, so as you get away from the center, you get closer and closer to 0. You never quite get there. So normal distributions, one of the reasons they're so special in real life is because the cumulative effect of many small individual processes produces normal distributions. When you add up a bunch of little random factors that don't think any of them individually have a big impact, but all of them together have an impact, then you get a normal distribution. And since you're adding up all these influences, that's essentially a consequence of the addition rule. There are lots of paths that go to the center. So if you can think, remember we were having a branching diagram with the blue and pink smiley faces of things going left and right as you went different kinds of families. In this case, if you drop a bead down here, this is called a Galton board. If you Google Galton board, you can see some YouTube videos of it. So some of the beads bounce left, and then right, left, right, and there's lots of ways you bounce left a bunch of times, and then right a bunch of times, and end up in the middle. But you have to bounce only to the left to get all the way to the edge, and you have to bounce only to the right to get to this edge. So there are more paths to get to the middle and fewer paths to get to the edge. So you get this bell-shaped curve. Just like when we're rolling the dice, there's only one way to get a 3. There's only one way to get an 18, but there are lots of ways to get a 10 or 11. And so if you imagine a ridiculous number of little beads and a very, very large number of these partitions that they smooth out, you get what looks like a normal distribution. And here's some other examples of normal distribution shapes. So this one has a mean of 0 and a standard deviation of 0.2. So since its standard deviation is small, it's skinny. This red one has a mean of 0 and a standard deviation of 1. So it's a little fatter. Because the area under each of these curves, under the green, under the yellow, under the red, under the blue, the area under each of those is 1. So if it's broader, it has to be lower at its highest point. And it can be shifted so that they have different different centers, or it can be raised and lowered. But what's really cool about the normal distribution is that shifting or stretching doesn't change their fundamental shape. So you can think of them as zoomed in or zoomed out, but they're not like deformed in any way. So one standard deviation away from the center is about 1/3 of the value. So 2 standard deviations, the area within 1 standard deviation is 2 standard deviations wide, and that has more than 2/3 and about 70% of the values of the value of the distribution. If you go 2 standard deviations, so that's a total of 4 standard deviations across, then you have 95% of the values. And we'll learn a little bit more about standard deviation next week, but the idea here is that most of the distribution is crammed in close to the center. The other thing that's cool and useful is the uniform distribution. So like the normal distribution, it's continuous, but unlike the normal distribution, all outcomes within a range are equally likely. There aren't any real world examples of uniform distribution. So like the coin flip gives you discrete uniform distribution with only 2 outcomes. The 20-sided die roll that we did gives us 20, so it's getting closer to continuous distribution, but still not continuous. This is an ancient, many thousands of years old die from Greece. You can see they were already rolling 20s back then. And so just like the normal distribution, if it's narrower on the x-axis, then it has to be higher on the probability mass function axis. But the area under each of these curves is 1. And like I said before, if you just had like a tiny sliver here, if the only possible outcomes were like between 2.5 and 3, then since the area, the width here was 1/2, the height would have to be 2. So the probability mass function can go over 0, but the area underneath it is still going to be 1. So remember, these are not probabilities, this is the probability mass function. And so this height is exactly the distance between these two things. So since this is 4 and that's 1, this height is 1/3. Since this is 0 and this is 10, that height is 0.1, and so on. So you can just figure out the height by the 1 divided by the distance between the upper end and the lower end. Finally, another distribution that's super useful but not as easy to wrap your brain around is the chi-squared distribution. Now, we talked about this normal distribution before, and the chi-squared distribution is basically what happens when you take things from the normal distribution and you square them so that the negatives are no longer negative, and then you add them up. So if you take one observation from a normal distribution and you square it, that sum is a value of the chi-squared distribution with 1 degree of freedom. If you took 100 squared values from the normal distribution, that would be an observation from a chi-squared distribution with 100 degrees of freedom. And these actually come up very frequently in the case where you have an observed count and an expected count, and you want to know how far away your observed count is from your expected count. And that's a situation where our horribly racist friend Carl Pearson came up with this plan, and then anytime we have squared distances, those are also chi-squared distributed. An important distinction is this is the Greek letter chi. It is not pronounced chi. It is sometimes spelled chi, but if you talk to any sister in Alpha Chi Omega and you ask her how things are going in Alpha Chi Omega, you will probably get ridiculed, and with good reason. So please do not call it chi. You can call it the chi-squared distribution. Please don't call it the x-squared distribution either. This is the Greek letter chi, even though I just hit Shift-X. It's one of those things that makes you look like a noob if you say it wrong. So here's some chi-squared distributions. So this is why it's called a family of distributions, is because they're not necessarily all shaped the same, but they have underlying math that's the same. So when you only have 2 squared values, probably they're going to be close to 0, right? But there's a chance that some will be big, because you're pulling from that bell-shaped distribution. But as you increase the number, the chances of all of them being really small are low, and so you get closer to this. So here's the 12 degrees of freedom squared values, and you can see that the mean is getting closer to 12. So it becomes more and more like sort of a normal looking distribution as you vastly increase the sample size. So that's the last distribution I want you to know.